some interesting ones over here. Actually, I just thought of one that I forgot to add. Someone has been very nice and found some Maclaurin series for sine and cosine for a natural log of 1 plus x. And we've used this one a lot, right? And we've kind of used this one, at least I proved this one, right? What we're going to look at now is a bunch of questions, 6, 7, 8, yeah, questions 6, 7, and 8, which basically say, find the Maclaurin series for a function, but use this information to help you. So for instance, if I wanted to find the Maclaurin series for x squared, the cosine of 1/3 x cubed. If I try to do that, by creating it from scratch, it would be horrendously difficult to do. Can you imagine how messy the second, third, and fourth derivative would be? And even although you're going to evaluate them all at 0, it could be quite hard to see a pattern. And so in many cases, we don't actually find things from scratch. What we try and do is use building blocks that we have spent some time and effort getting and do this one. So the building block I'm going to use is this fella. So I'm going to focus on just getting the power series of this guy right now. Well, isn't he the cosine guy? Now, we've done this trick with this. Don't you think of that x as just being a placeholder rather than its x? So if I substitute, replace this x with 1/3 x cubed, I will have its power series. And its power series will be n equals 0 to infinity, -1 to the n, whatever I have, in this case 1/3 x cubed, raised to the power of 2n, and on the bottom, 2n factorial. Are you comfortable about how I got the power series of this guy using that as my template? Right. I'm replacing this x with 1/3 x cubed. So far, so good? Now, there was a second piece to that. There was an x squared, but don't I just stick the x squared there for the time being? That's not a biggie. Now, I'll just leave my x squared here for a little bit longer. You know that style point says you're not allowed to just leave a sigma in that ugly format. We don't like this. So I am going to take this out, which is 1/3 to the power of 2n. And I'm going to take this out, which is x cubed to the 2n. And I'm going to do 2n factorial. And again, I'm probably going to end up doing more lines that you would want, but I kind of want to show you all the steps here. X cubed raised to the power of 2n now gets you x to the 6n. 2n factorial, 2n factorial. Is there a better version of 1/3 to the 2n that I could use? A nicer looking version of it.
Bring the 3 down to the bottom of the fraction, raise it to the power of 2n.
And I guess I shouldn't have had that big gap now. And to finish, once the dust has settled, bring the x squared in and add it on to the x's that you've got. And you now have the power series for this guy. Does it have a flow to it that you feel comfortable with? Take the cosine, replace the x with, in this case, 1/3 x cubed. Make it look pretty. And you're done. That particular question is very similar to number 7. Are we good? Right, the other two questions are x squared, the natural log of 1 plus x cubed, so you would use this guy. And the other one is x cosine of 7x, which would be using this guy again.
On the last step of that problem that we just did, is the -1 supposed to be to the power of n?
Yes, I just missed it. You're right.
Thank you.
Are we good? Oh, be careful, Maggie. Come on, girl. Have your butt. There she goes. She's under my desk with lots of cables and she got one caught around her leg. Okay. Going to do another group of questions in a minute, and specifically we're going to look at Taylor series. But just to give you a little insight to show you how powerful power series can be. If you took all the even powers, which is a cosine, and all the odd powers, which is this one, and I wrote these guys down, cosine of x would look like this. It'd be 1 plus x squared over 2 factorial, let's get this right, minus, there we go, plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, forever. And if I wrote down the power series for sine x, it would start with an x over 1 factorial, minus an x cubed over 3 factorial, plus an x to the 5 over 5 factorial, plus an x to the 7 over 7 factorial, forever. And now I'm going to put in e to the x. And something weird happens. Do you know if you took the cosine power series and you made everybody positive, and you took the sine power series and you made everybody positive, and you added them together, wouldn't you get the power series for e to the x? Now that is an amazing result. What on earth is that telling us? It's telling us that e to the x is actually related to the sine and cosine function, but they're not related in the real world, the real number system. They are in fact related in the complex numbers. The e to the power of I, the square root of -1x, is equal to that. And that's called de Moivre's theorem. And that particular piece of information, you can understand where it comes from by looking at the power series. And this weird piece of information allows us to do all sorts of trig identities. Have a look at it online if you've got time and the exams are over and you want to see some cool stuff. De Moivre's theorem. You'll find that you can use this trick to discover how trig functions work when the numbers are complex numbers. You know, like what's the sine of 2i? What's the cosine of 1 plus 3i, right? Complex numbers. And it's just mind-blowing what these things do. Now, not in a test question, but it's just overwhelmingly interesting that what we think functions are and what we have analyzed them to be are not quite the same. A sine function is just an infinite polynomial. In fact, so is pretty much every function. Some of them are more useful than others, but nonetheless they are. Okay, time for our last guy. Taylor series. for some function f of x. It's a power series as well. But it's going to be centered at x equals a. So what will that look like? You will find the nth derivative at a, not 0. The x to the n will now become x minus a to the n, but the n factorial will be just as it was. Now, if I write beside that what the Maclaurin's series would look like, oops. Isn't the Maclaurin series just the Taylor series when x is 0?
When a is 0.
Yes, when a is 0. You're right. When a is 0. So Maclaurin, and I've no proof of this, but I'm assuming this is what happened is Maclaurin figured this out, and it was really useful. And in fact, when you look at power series, they tend to use Maclaurin series because would you agree power series with x's and x cubes are just easier to deal with and look pretty. And then Taylor came along and said, hey, you know, you don't need to be centered at 0. You could be centered at 4 or 42. And this is the power series that you get. So quite a lot of overlap. Would you agree that this is just a special case of this one? And so all the things that we've been doing with this, we can also do with this. So can't we find radius of convergence, interval of convergence? Can we even find the power series as well from scratch if we had to? So we're going to kind of duplicate a lot of the things that we've done, right? We're just going to, what would I say? Recreate the wheel. So let me see if I can start with, question similar to 9. Here is our function that we are going to do a Taylor series for. And it's going to be centered at a equals 2. Let's see what that looks like. Well, I have to kind of go over here and use this guy. So it's going to like be a 2-tier stage. What do I mean by a 2-tier stage? I am going to be looking at, at this guy, and we're going to be looking at how you would create a power series. Bearing in mind, I already know the power series for this centered at 0. So my answer should look similar to that. Would you agree? For instance, won't this x be x minus 2? Great. So, does anyone want to have a hazard a guess? It's not a very good word, hazard a guess. Anyone want to have a shot at what you think that should be? No guesses yet? Should look like this guy. Great. With changes. Okay, let's look at this guy. There's an 8 here. You agree? How am I going to cope with that 8? Let's fix it one little piece at a time.
Just factor it out.
Yeah, stick it over there. So basically, I'm going to think of it as this guy, right? Now, over here, the power series for, oh, I'm looking at the wrong damn thing. I apologize. I don't know where my brain is. Here, right? This is the guy. What's the substitution that I would be using to get a 1 plus x in this guy?
Negative x.
Okay. So you would have a negative x. You do it to power of n. Great. I don't need actually brackets now. So it's going to be 8, n equals 0 to infinity, negative 1 to the n, x to the n. Now that would be great. In fact, wouldn't that be the power series, or it will be in a minute? Wouldn't this be the power series at a equals 0? Great. A equals 0. Now, I don't want 0. I want to know it at a equals 2. So we need to figure out what to do next. What do you think I'm going to do next?
Substitute that x minus 2 in for the x.
So it would seem reasonable. Does that seem like a logical way to tackle this problem? To basically treat it like a Maclaurin series first, and then essentially do a substitution. And that in this particular case, at least, that's the substitution that we got. I'm over here trying to look at this fella if I can. Not, come on. I was going to show you something, but I can't make the damn thing behave. It's been awkward today. Okay, there we go. Okay. Oh, I apologize. We've answered the nice question, but it's not the question that they wanted. They just wanted the first 4 terms. So, pretend I didn't do that question. I was looking at the thing and I was going to show you their solution, but they didn't tell me that. So, okay, we got to do what we got to do. Okay, so let me do a question where we do the first 4 terms in. I'll just pick something up. How about f of x is a natural log of x, and I'm going to do it centered at 7, and I want the first, I'm only going to pick the first 3 terms because it takes forever and a day to do that. And we're going to do it, obviously, a Taylor series. So I need the first derivative, which is that. Which you can write as x to negative 1. I need the second derivative, which is negative 1 x to negative 2, which becomes that guy. I need the third derivative, which is positive x to negative 3, which becomes that guy. Okay, now, that's a special case, the f of x. If you plug a equals 7 in here, won't the first derivative at 7 be a 7th? Won't the second derivative at 7 be negative 1 over 7 squared? And won't the third derivative at 7 be positive 1 over 7 cubed? Are we all happy with the pattern? Right, now, f of x then is sigma, typically n equals 0 to infinity, the nth derivative at a, x minus a to the power of n over n factorial. If you write it out in full, it looks like this. The value of the function at a, because that to 0 and that to 0 are 1. Then you get the first derivative at a over 1 factorial, the second derivative of a over 2 factorial, and since I'm going to the third term at a, x minus a cubed over 3 factorial. This guy, if you plug in 7 here, is log 7. This guy is 1/7 x minus a. The one next door to it is negative 1/7 squared over x minus a squared, all over 2 factorial. And the next one to it is positive 1/7 cubed. And I'm saying x minus a. Shouldn't I be calling it x minus 7 because a is 7? That is the terms written down. Basically, what, the first 4 terms? Okay, the first 4 terms. The value of the function at a, the derivative of a, x minus a over 1 factorial, which is this guy. The second derivative at a, x minus a squared over 2 factorial. Third derivative at a, x minus 7 cubed over 3 factorial. Now, technically speaking, this question's not finished. Shouldn't I be making these into numbers and writing them down as ugly fractions?
I have a question about your third derivative.
This one?
If you
Okay.
go up to where you actually have the f
Oh,
prime,
you're
shouldn't that
right.
be 2x?
You're right. There should be a 2 there and a 2 times 3 there. I missed it. You're right. What will that do? It'll make that a 2, and it'll make that a 2 times 3, and off you go for the rest of the universe. Okay, I'm going to reset these guys up again. That's the correct answer, which I did get. The second derivative at 7 is negative 2 over 7 squared. The third derivative at 7 is positive 2 times 3 over 7 cubed. If you went and found the fourth derivative at 7, it would be 2 times 3 times 4 over 7 to the 4. I'm now going to add in a 1.
I don't agree with your second derivative, and I'm not sure if I'm just not seeing it.
Okay, let's see. I'm 1 out. I am 1 out. That'll be a 1. That'll be a 1 times 2, and that'll be a 1 times 3. So that'll be a 1. That'll be a 2. Yeah, and then it'll be 1 times 2 times 3. And of course a negative. Oh God, I am not on my form today. I have no reason to do that. I think my brain is too busy thinking about what is happening after this question. Okay, that's a neat version. I did this earlier. I should stop doing things in my head quickly. I am not good at it. Right. Let's suppose I would like to get the Taylor series for this same function centered at 7. Then, according to our formula, it's n equals 0 to infinity. The nth derivative at a, x minus a to the n over n factorial, right? essentially, to get this, we need to find what the nth derivative at 7 is. So we got to look at this pattern. And we are going to have to figure out what the nth derivative would be based on what we can see here. Right, so would you agree that the answer goes plus, negative, plus, negative, plus, negative? And whenever you see a plus negative thing, don't you get a negative 1 to the n, or you get a negative 1 to the n plus 1, right? One of those two is going to do it. So to figure out which one of those two works, why don't I just randomly choose this one, which is n equals 3, right? The third derivative. If you plug 3 into this, won't you get a negative answer? So it's not that one. If you plug 3 into here, don't you get a positive answer? Because negative 1 to the 3 plus 1 is negative 1 to the 4, it's positive. So I now know that I have that piece. The second derivative has a 7 squared on the bottom. The third derivative has a 7 cubed on the bottom. And the fourth derivative has a 7 to the 4 on the bottom. What power of 7 would the nth derivative have at the bottom?
N.
Now, the reason I added in an extra 1 here is this guy on the top is really 2 factorial. This guy in the top is 3 factorial. This guy in the top is 1 factorial. Are we good so far? Now, what will the nth derivative have on the top? What factorial will it have?
N minus 1.
That now means I have the guy that goes here. It's going to be negative 1 to the n plus 1, n minus 1 factorial, over 7 to the n. The x minus a becomes x minus 7 to the n, and the whole thing is over n factorial. So we are looking at negative 1 to the n plus 1, n minus 1 factorial, x minus 7 to the n, and on the bottom I have these two guys. Is there any simplification that is possible here?
The factorials.
And when you do that, what's left behind?
N on the bottom.
And then I am going to just go n equals 1 to infinity. And you might say, why am I not doing 0? Wasn't f of 7, I've lost the damn thing, wasn't the original function at 7 the log of 7? That doesn't fit the pattern. So all you do is put that at the front. In other words, put the value of the function at 7. And it's separated because it doesn't follow the generic pattern that everything else does. And that's not very common. Most of the time, the power series works for everybody. But in this case, you had that little hiccup. The f of 7 goes first. And there we are. Do you see my formula for the thing when you write it out in full? Isn't there f of a? In this case, f of 7, and then the rest. And because that is a log, a weird log that doesn't really match anything, you put it here. If I made n equals 0 and I plugged 0 in where all the n's are, the answer I get would not be log 7, right? Wouldn't be anything particularly useful. That is the kind of the ultimate version of difficult. So one more example of that process, but I'm going to pick an easier one just to show you that they aren't all horrible. And you are going to have your thinking caps on so that you catch me when I screw up early. We're going to do this fella, and we're going to do him centered at 6. And we are going to find the Taylor series. So I have my function, and I'm going to evaluate it at 6, which is what, e to the power of 12. Interesting. I'm now going to find its first derivative, which is 2e to the 2x. And if you evaluate the first derivative at 6, don't you get 2e to the 12? Now I'm going to continue to do derivatives until I think I can see a pattern. Now the next derivative, wouldn't it be 2e to the 2x times another 2? I'm not going to write that guy as 4. I'm going to call him 2 squared. And it's always a good idea not to calculate the thing in full, but just to write down what the calculation is. So in this case, it's 2 squared. And that gets me 2 squared e to the 12. And if I do the third derivative, it looks like that. And the third derivative evaluated at 6 looks like that. I think I can find the nth derivative at 6. Would you agree that the pattern this time is really quite nice? Okay, won't all of them have an e to the 12? And don't all of them have a power? 2 to the power of what would be the nth derivative?
Power of n.
Right. Now, if I go back here and call this guy 2 to the power of 0, doesn't he fit the pattern? So I don't need to suck him out. Remember the other one had a log 6 that didn't fit the pattern. You had to suck him out and then do the rest. In this case, he is fine. So Taylor series says that it's n equals 0 to infinity, the nth derivative at 6, x take away 6 to the n, all over n factorial. So in this case, it's going to be n equals 0 to infinity, this guy, would you agree that one was just so much cleaner than the log one? The process is the same. Don't you just keep finding derivatives until you can say, I see a pattern, I can now get the nth derivative at, in this case, 6. Because if you've got that guy, he goes here, and the rest is pretty standard. And maybe you'll get a cancelling, maybe you won't. In this case, you don't. If the first term, the value of the function at, in this case, 6, if it doesn't fit the pattern, then you suck it out and you put it here and you start at sigma n equals 1 to infinity of whatever you get. And that would be the log version that we did earlier, right? So depends on what you get. If something's not going to fit the pattern, it's typically the first one that doesn't fit, right? Everything else pretty much moves in to that. Actually, that one went correct for a change, so I can do questions correctly. Sometimes. Actually, the question I've just done was the last one, question 12. So I'm going to just spend a few minutes here looking at finding patterns, because that's a skill that you don't get a lot of practice at. So I'm not even going to tell you the function is, because it really doesn't matter. Suppose I find a function and it's a Taylor series and it's going to be evaluated at 2. And that's all we have. And I want to find the nth derivative at 2. So we have to be able to recognize certain things. Do you recognize who this guy is? And if it helps, I'll stick a 1 at the front. Do you recognize it a little bit better now? Who are these guys?
N plus 1 factorial.
Oh, well, you're right about the factorial. Wouldn't this be 5 factorial? This would be 4 factorial. This would be 3 factorial. And this guy would be 2 factorial. So you're right about the factorial. But is it n plus 1?
N plus 2.
Right. Have you noticed that the third derivative gets you 5? The second derivative gets you 4. So this would be n plus 2 factorial. Okay. Well, let's pretend that the question was more than just this, but it was a fraction. So it was this over try to think of some here. It's unfortunate the 2, but it's this over 2, this over 2 squared, this over 2 cubed, and this over 2 to the 4. Good on. What's the nth derivative now going to look like at 2?
Two to the n.
Is it just n? The third derivative gets you 2 to the 4. The second derivative gets you 2 cubed. And the first derivative gets you 2 squared. Would the nth derivative get you 2 to the n?
Be 2 to the n plus 1.
Right. Now, do you see that sometimes you do get 2 to the n, right? But couldn't you also get 2 to the n plus 1 or even 2 to the n minus 1, right? If you have figured this out, then you should be able to put the package together. Since my original function is fitting the pattern, I don't need to kick it out, right? I can start at 0. This will give me n plus 2 factorial over 2 to the n plus 1 times x minus 2, right, to the power of n, all over n factorial. And then we need to make it look pretty. Can we do any cancelling here? And be careful. Can these factorials cancel?
Can you do it's going to be n plus 1, n plus 2 at the top.
You nailed it. It's exactly what that's going to be. So can you understand where he was getting that answer from? That you can cancel factorials right? You just have to cancel them a slightly different way. The algebra of cancelling factorials is not quite the same as, you know, other cancelling. And quite rightly, that is the answer. So for those who are not sure where the heck did that come from, here is one way to look at it. N plus 2 factorial is 1 times 2 times 3. And yeah, you finish it that number. But the one that would come just before it would be that one, for instance, right? And the one that would come just before it would be that one, right? And n factorial is 1 times 2 times 3. And we'll finish at n. And the cancelling all happens here. But these two guys are left on the top. Does that help? So say hi right now, because what we're going to do now is spend a few minutes talking about your test that's coming up and what is in it and what is not in it. So give me a few seconds to kick back in here. Been a hectic couple of days, so I haven't put it up yet online, but I will be. And what will happen is that when you turn up, oh God, will it be today? I'll try my best, but I have another class and I have a 2-hour committee meeting, so that's going to keep me a while, and I still have to get your videos up. So late this evening, right? You will have this up, and what it will basically be is the same list of information that you got in test 1. There will be a link to the Zoom meeting that you'll turn up on. We all know that the test is on Monday, right? And you're going to do exactly the same rules as before, same time. It's going to be in WebAssign. It will just appear, you know, 1 second after 11 o'clock, and you've got until 12, and then you've got 12:30 is your upload into Canvas. And if these times don't work for you, then you just, you know, contact me and we'll figure another one. And what else can I tell you about it? Oh, let's tell you what's in it. It's useful. Your test, oops, I just picked the wrong one. Getting good at doing this today. It's covering the last 2 weeks. And your test is going to have, I'm very bad at multitasking. Where the heck are you? Oh, here we are. There we go. It's going to consist of, it says, strategies for testing, power series, representing a function as a power series, and Taylor's and Maclaurin series. But the strategy for testing is optional homework, and you got 0 points for it. So I'm not going to test you on strategies for testing. And in fact, it's a good section to do when you're coming to do the final, because it basically gives you a whole load of different series that you need to test convergence for. So you're just going to get power series, representing functions as power series, and Taylor's and Maclaurin's. So it's only 3 sections. And the application section that would have been in this test, we just never got around to doing yet, so I'm just pushing it on to the next test.
So the ratio test isn't on the test?
The ratio test is not in your test. It's been gone and went. I will make up for that by making sure you get a question in the final. So you will get it tested at least once. But it's not a problem that I missed out the ratio test, because aren't you going to do the ratio test in power series anyway? So it's not like you're missing it. You're just getting it in a different place. The questions are pretty long, so don't expect a lot of questions. You're definitely getting 3 questions. That's 1 from each section. You're not getting 6, so my best guess is 4 or 5 questions. I haven't made the test up. It depends if they're big. If they're big, you'll get 4 questions, you know, if they take a long time. If they're a bit in the short side, then you might get 5. And they will be in chronological order. So you know the last question is Taylor's and Maclaurin's, and the first one is power series. Anything else you need to know? Oh, homework is up to and including 11:10. Anything else? Are we good? I don't know if no questions is a good sign or a bad sign. I'm being an optimist and I'm going for it's a good sign. If I'm going to hang about then for the next few minutes, so if you've got a question that you don't want to share with the others, or you've got a homework question, that'll work as well. We can talk about it. I suggest strongly that you have, if you don't already have, some formula like Maclaurin's and Taylor's series written down somewhere at the side, so you can just look at them when you need them, rather than trying to memorize. Well, it'd be better if you did memorize them, but you know, as an aid to the memory, that would be good. Right, bye-bye, guys.
You.
Okay, who wants to go first? I've got a lot of customers today. I should charge you extra. Okay.
You're going to charge spectators?
Yeah, well, you're the audience. They should pay, you know, they should pay money. Okay, somebody's got to go first, so just jump in. You know, there's not a list here, so who's going first?
I'm going first.
Okay, Emma, you got the job. Go for it.
So, we were covering a question similar to question 9 today.
On what section?
It was a Taylor series. It was like the first Taylor series.
Okay, right. Do you have an example of one, and I'll just do your example, that way I can keep it consistent to what you want.
Oh, well, I thought you could just like root around for the piece of paper that you did, because
Oh, I can root around for the piece of paper I did. Okay, and it was question number what? Like, say that number again?
9.
Oh, 9. Okay. Well, I had this piece of paper, which isn't 9. Is it the log x one?
No, it was 8 over 1 plus x.
Okay, 8 over 1 plus x.
Was that the one where we solved for the round thing accidentally?
That is the one we solved for the wrong thing. Okay, then let me solve for the right thing. In question 9, I believe you were asked to find the first 3 or 4 terms.
Oh, okay.
And that's not find the entire equation. So that's the mistake.
We never finished finding the series for number 9, did we?
No, but we weren't asked to, so I guess
Okay.
I stopped.
Okay.
Right, so.
Yeah, that's a lot.
Okay, that's just me being careless today. Although I kind of finished better than I started. So all you've been asked in this question here was to do the first 4 non-zero terms. And that was it.
Okay, thank you.
So what you would do there is you'd find the original function, the first derivative evaluated at 2, the second derivative at 2, and the third derivative at 2, and then just plug them into the general equation. I've lost you guys. Where are you? There you are. Whoops. Yeah, yours always began. My window was wrong. So in this question, what you would do to solve that problem would be essentially you'd find the value of the function at 2, the value at, right, those guys.
Mhm.
And then you would write down the value of the function at 2, and then the derivative at 2, x minus 2 over 1 factorial, the second derivative at 2, x minus 2 squared over 2 factorial, and then the third derivative at 2, x minus 2 cubed over 3 factorial. So you're not looking for a pattern, you're just trying to find out what these numbers are and replace them here. So, well, I can do the first one. It's 8/3. Can we just pretend that's 5, 7, and 10, just for argument's sake? Then your answer would be 8/3, 5 of that guy, 7 of that guy, and 10 of that guy. Now, it's not quite finished because won't you have to turn these into numbers and simplify? So if these were really true, you would have 8/3. Then you'd have 5 lots of this one. That would get you 2, so you'd have 7 halves of this one. And 3 factorial is 6, and 10 over 6 would be 5/3. And that would be the first 4 terms. And just to make life awkward, your answer wouldn't have pluses. They just tell you to put commas between them. So you're basically just writing down what they were equal to separately with a comma. I don't know why they didn't just say stick a plus there, but they didn't. So just so that when you write the answer in, it matches what they've got. Because if they don't, if you don't do that, it'll probably say you're wrong, even though you're essentially right. Okay, what's next? What have we got? Go for it. What you got started?
Okay, I got question number 13.
Okay.
From,
What section? Yeah.
Believe it's 11.8.
Okay, do you have the question itself handy?
So it's sigma infinity to n equals 1. With 7x minus 2 to the power of n over n to 7th power. No, it's n. No, wait, n times 7 to the power of n. There we go.
Something like that?
Yes.
Okay, what have you been asked to do here? Radius and interval, your convergence, I'm guessing, but I don't know.
I'm double checking real quick before, because I somehow managed to solve the problem, but I was completely lost of how to do it. So
okay, we can show you.
Yeah, it says find the radius convergence for R of the series.
Okay, so just the R, that's fine. So we're going to do the ratio test. And
then it also says find the interval of I of
convergent series. So they do want both then. Okay. Yeah. So we're still going to start with that. So that's good that we don't need to change that. This becomes 7x take away 2 to the power of n plus 1. The n that you said on its own is n plus 1. And the 7 becomes 7 to the n plus 1. And then you turn these guys upside down. You essentially get that. Now, there is an obvious problem here, and that's that 7x minus 2, which isn't typical, right? Isn't it normally x, like x to the n, or even an x minus 2 to the n? We'll fix it. It's fixable. Let's do the cancelling first. Let's simplify it down as much as we can. And then we'll worry about what's going to happen afterward. I can't really do anything about the n and the n plus 1, so I'm just going to write them down. Won't the 7 to the n cancel the 7 to the n plus 1? but won't that leave a 7 on the bottom?
Mm-hmm.
So I'm going to stick the 7 here and put a little bracket around it. Is it okay to just leave it in the bottom like this? Now, if you cancel all of these guys with all of these guys, don't you get left with a 7x minus 2 on the top? So you get left with that guy. So far, so good?
Mm-hmm.
Now, you've hopefully done enough of these ugly fractions. What will n over 7n plus 1s get you when n goes infinite?
Would it be 0?
Not this time. There's an n on the top and there's a 7n on the bottom.
So wait, if n's on top because n goes to infinity, and you had 7n on bottom, so 7 times infinity would be infinity. But wouldn't infinity on the bottom of a fraction still make it equal 0?
What you're not doing is you're not realizing that you have to divide top and bottom by n first before you start making things infinite.
Okay.
If you make it infinite here, you just get infinity on the top and infinity on the bottom, in which people say, well, I know what that is. But if you do the technique, divide top and bottom by n, what you transfer it into is...
It'd be 1/7.
Yes. Okay, that's what I was getting at, right? So
yeah,
you got it now. So we have a 1/7, the absolute value of 7x minus 2. It's kind of cool, kind of interesting. Couldn't I bring the 1/7 inside the absolute value because it's a positive? And so if I distribute it, don't I get that guy? Yep. Absolute values are just basically saying it's a positive thing inside, right? You make it positive. And isn't a positive number, you're allowed to bring it inside. Now, according to the ratio test, shouldn't that be less than 1 if it's going to converge? So I now have my radius of convergence. And I also in a few moments will have my possible interval of convergence. Because if the absolute value is less than 1, doesn't that mean the thing in the middle is between 1 and -1? So how do I get an x in the middle on its own? Because that's what we really need.
Plus both sides by 2/7.
So that's going to get me 9/7, and that's going to give me, I believe, -5/7. And in the notes, you'll see I call this thing something like our possible interval of convergence. So what do I now need to do? This is what the interval of convergence might be, but how do I find out what it really is?
Do you plug it in for x?
Right. So I plug in 2 values, don't I? Plug in that fella, and then I plug in this fella. For time reasons, which one of the 2 do you want me to check? And I'll just do the check on that one.
Let's do the negative.
Okay. So if we go to the original, which is this guy here, and you make x is -5/7, what you get is sigma n equals 1 to infinity 7 times -5/7, take away 2 to the n, all over n times 7 to the n. Seven times that guy gets you -5. -5 take away 2 gets you -7. So you now end up with that guy. Right? All of this in the middle ends up being -7. If you pull out -1 to the n and 7 to the n, you now get That guy. And I can simplify this fella. To that fella. So here's the question. You hopefully can recognize that guy. Do you recognize it as an alternating series? It's actually a very simple one. Do you know whether it converges or not? Can you remember? Does
Not off
anyone?
the top of my head.
Yeah. It decreases to 0. You can prove that its limit is 0 and it decreases. So what does that tell you?
What's it? Do we have to do derivative?
Well, you could. I'm just telling you I've done it.
Oh.
And I've done it and I know that its limit is 0 and it decreases as well. So what does that tell us about this series then?
Oh, it
Converges, right. Which means you go back up to here and now you're allowed to use him, so you get a square bracket. And can you just trust me that the other one diverges? It ends up being a harmonic with pluses. You know, it ends up being sigma 1 over n. So that is you finished. You have now completed the process. Now, I want to show you a different attack to this line. Just a different way of doing it. So we got this guy and it's less than 1. That means this guy is less than 7. Agreed? Now, divide everybody by 7. Why do you need to do that? You only get radius of convergence when this is x. The radius of convergence is not 7. The radius of convergence is a number that you have here when that is 1, right? It's either absolute value of x in the easy ones, or it's x minus 2/3 in the harder ones, but it's always got to be x. So can you see, we end up at the same place algebraically, and we get the same R value because of that. But I just, in this case, I multiplied first and we got it. In this case, I divided everybody, but we still got it. The rules about as long as you do it to both sides still work with absolute values, right? You can still divide both sides. You can still multiply by both sides. The only rule is you must make sure that it's positive numbers that you're doing it with. So you can divide both sides by 7, nothing wrong with that, right? You can multiply both sides by 4, nothing wrong with that, or 4/5. And that's how we kind of manipulated it, essentially to make sure that's an x. Okay, who's next? Who have we got?
Douglas and I are both spectators, so.
Nothing wrong with being spectators. James, you got a question?
Yeah.
Are you sure it's the real James and not the pretend James I'm talking to here?
Let me think about that.
If you have to think about it, we're definitely in trouble.
Well, I guess I could have just recorded this.
Which case you'd have to time my answers. So I've just said tralfamadon. What word did I just say?
That's not in my artificial intelligence.
Okay, what's your, do you have a question?
Yeah.
Okay, what you got?
So if I have a series that's n to the minus 1 to the n times n squared. I know that diverges, but
yeah. How would you prove it?
Yeah.
If you take the real valued part of it, which is basically that guy. Right. It's not too difficult to find its derivative. And is x greater than or equal to 1? Yeah. Isn't that positive?
Mm-hmm.
And doesn't that make this increasing?
Yeah.
If you have an alternating series that is increasing, it diverges.
Okay. Makes sense. I was gonna try and see if I could do the limit and see that since the limit wasn't 0.
That would work too, because its limit is infinite, and that'll kill it.
Okay.
So both are very justifiable proofs. You don't need to do both. One is enough to prove that it's diverging.